Yeah. The first song was, we would play that at our dance parties in the dorms back in the early 90s. Okay, so the due date for the extra credit. I think I'm trying to tell you to get it done while it's still fresh in your mind, but I'm not going to close the assignment in an arbitrary fashion if you've got other things going on, right? But for it to be effective, right, meaning for it to be worth for you to do the assignment so that you do well on the final exam and in the next midterm, I think you want it done in 2 weeks, right? What I mean, in any course, there's things that have points, right? And then there's activities that you do that might not directly relate to a point, right, or credit, but might actually be some of the most important things you do to actually learn the material and thus get a good grade, right? So the reason why I want you to do it as soon as possible, but correctly, right, is so that'll mean that it's in your brain for a longer period of time, so that when it comes time for the final exam, you're not rushing around, right, trying to cram it in there. And 110 does not really lend itself to cramming. It's actually just a few big ideas that once you get, then everything flows from there. But until you get it, it can appear like a grand mystery. Okay. So just like my karate example, that if I got a tournament in April, I want to learn my form as soon as I can so that my mind and body has time to digest it, so that I don't embarrass myself during the tournament. Okay. Still good question. So we've been talking about synthesizing circuits, right? Or synthesizing a transfer function with circuits, I should say. And we talked about, like, this is because this transfer function or mini transfer function is being multiplied by this mini transfer function, right? We could, oops, that's a plus. That's the minus, right? We could just almost write it out exactly like this, where this mini trans function comes from here, and this one comes from there. The reason why it works is that these op amps isolate these R's and C's, right? Because if we just did this, okay, which would make a filter, but everything depends on everything. So this output here depends on that capacitor, these two resistors, and that capacitor, where this transfer function only depends on these two. This transfer function only depends on those two components. Right, it's a passive filter, and believe me, they're used, right? But what you tend to do is find a chart of passive filters that you can use. They're actually kind of difficult to analyze. All right. So the next thing we need to talk about is parallel synthesis, right? So, and where this is headed is that we're going to use a very advanced technique to synthesize filters that kind of uses all three. And so we do the series, we're going to show you the parallel and then the feedback, and then it all kind of gets tied together at the end. All right. Well, what if I wanted this? How would I get it? Right. Which converts into this, right? Well, actually, I'm going to let that be for right now. But you could sum these up, right? So how could I add these two together? Well, you use a summer. And in this case, they're both positive. Right? It'll just be easier to use the advanced summer technique, right? We have these transfer functions. They're all multiplied by 1, right? So we want a gain of 1, so that's +2. So we have to add 2 dummy resistors. All right, everything's 100K in that case. Now, sure, you could add 1 resistor, 50K, and it'll work out, but okay. But that's now this, you just multiplied it together and everything kind of stayed the same, right? There was a pole at -10, a pole at -1,000, and a 0 at 0. But when I add these together, right, let's just right, I have to find the common denominator. So I just multiply each side by that. Okay. So yeah, when you multiply these two together, you're going to get the same, we get the same denominator. So we're going to get the same poles, right? But now we're going to have S plus 1K plus S plus 10 times 1K. All right. So we're going to have a much more complicated numerator. All right. Now, what I'm actually showing you here, right? Take 2 transfer functions and add them together. We actually don't do that much. What we do is we use this technique as part of something else that I'll show you later. All right. But probably the most common parallel architecture is the RLC circuit. I'm going to go over a little bit more, but basically, if I have VL plus VC divided by the V total, I can come up with a transfer function and see how that's this plus that. But this plus that is just taking the output voltage from here, right? Now I'm going to go into this in more detail later, but these circuits and these circuit elements in series, because it's one loop in a mesh, right? They all add linearly, right? And if I just take the output here, I get the high pass function of the inductor, the low pass function of the capacitor, and I get something called a notch filter, right? But we'll go over that later. Here, really what the important part is you can have signals coming out of op amps and that you would just add them with an advanced summer. Okay. Now, I want to talk about the feedback architecture. Oh, you know what? What I should have probably done is just say I have H1 S, H2 of S in okay, and they come out as a summer. That's the system diagram, right? And like in the series, right? Because we're in the complex plane S, right? If one thing flows into another, you're just multiplying these as you go along, right? Here, we're adding them. Now, we're actually going to, next thing, we'll have some feedback. Okay. Okay. So in this, we have a summer and we have some kind of transfer function, right? And we add in the input, we pass it through something, and then we subtract it. And this is called negative feedback. All right. Now, something is that I can take my out from node 2 here. I can take it from node 1. I can sum them for an output, and I can take their difference for an output. All right. So let's look at node 1 first, right? And I follow V in, and nothing, it's just in, there's no multiply, there's no divide. So node 1, so V1 equals Vn, right? Now, how do we deal with this here, right? So, in fact, this node here, right, is passed through HS And it goes around the loop, right? So it might seem weird, but V1 equals Vn, but it also equals V1 times the transfer function and then subtracted, okay? Now, kind of the way I've just mentioned it, it's all like, you might think it's happening all instantaneously, but really, there's a delay that it takes time for signals to go through the system. All right. So it's fine. Well, now let's collect V1 here. 1. Okay. And then we have V in. Oops. V1 divided by Vn equals 1 divided by 1 plus H of S, and whatever that happens to be. All right. Now, notice we have negative feedback, right, on the right-hand side. But when we collect the negative feedback to the inputs, it becomes positive. So, and then when we take the ratio, it's positive. So when you see this positive here, it actually means there's negative feedback. Okay. That might throw you for a bit, but so now what if H of S equaled 1 over S, right? It's the integrator. Okay. So we have V1 divided by Vn, our transfer function, right? 1 divided by 1 plus 1 over S, all right? Now this is a mathematically valid formula, right? But it's not in the proper polynomial format, all right? And you've got to put it in that where you might have something like okay, we have all the polynomials in the numerator, powers 0 or greater. All the ones in the denominator, powers 0 or greater. This is not in standard format, right? So yeah, I mean, this would be, if you left an answer like this would be considered wrong. So you have to manipulate it into something like this. Well, with experience, you realize, all right, let me multiply through by S. I get S plus 1, which is a high pass. Okay. That's pretty good. So this is the proper format. Okay. Now, yeah, I'm going to get into how to write it out when they're not just real poles and zeros. All right. So that's one way, one thing. Let's redraw it. But now let's take it here. Okay. We take the input, it comes in, and it's multiplied by h of s, right? N times h of s. Okay. But we also, we're going to subtract V2, but it comes through h of s as well. All right. So now let's collect our V2s. All right. And then take the ratio. And we have this. All right, let's do the same thing where h of s equaled 1 over s. So here we have 1 divided by s, 1 plus 1 divided by s. All right, we need to get it into that polynomial format. So we, in this case, we multiply it through, and we get the low pass. All right, and so we get the high pass and the low pass all at the same time, right? Which then I could add or subtract or do whatever I want to. All right. Now, how would I go about turning this into a circuit? Well, I have a summer, right? I need a summer, and I need 1 over s. Well, the summer, just going to have to trust my memory on that, right? I'm just going to draw out, assuming that I'm going to need the advanced summer technique. I'm just going to draw it out. Right. And I'm just going to choose 100K. Since I knew Vn isn't being scaled by anything, I want these two to be equal, right? And this is all on the assumption, right, that I can make that advanced summer work by using the architecture and adding the dummy resistor. All right, now, what about 1 over S? Well, there's a few ways to do that. There is the Deboo integrator, and that will equal okay. And you just select RC to give you the 1, right? Or we have the inverting integrator. Okay. Now, this is, you might think, but I wanted positive. And you say, that's okay. I'll put in another inverting stage. Right. But it turns out We don't have to. And it's just better if I show you. So I'm going to use the inverting integrator because it's the simplest thing. Okay. So this is my H of S, right? And so the black is my summer, right? Where I have something positive coming in and something negative coming in. The blue, I want to be plus 1 over S from here, right? And then I would subtract it, right? Because that's how the negative feedback, I need that negative feedback. So here would be my 1 over S, right? Which then I subtract. But this actually gives me minus 1 over S to begin with. So now, rather than inverting it and then bringing it on the subtraction side, no, I'll just leave it right here. Okay. And I'll make that 100K. This 2 RCs will be, if I used actually 100K and 10 microfarads here, that would give me minus 1 over S. Well, now I have plus 1 gain, plus 2 gain. Even though it's on a feedback, it's still the gain. So I need to add, again, just to see how it works, 100K and 100K, which of course is, those are in parallel, right? So you can put 50K, right? And now this node is here, and this node is here. So this is our low, and this is our high, all at the same time, right? And by using the advanced architecture, and here's the thing, this is true, this works, but it has more parts. And so if we're going to use a lot of these, an 8th order filter would use 8. So really, you want to keep it simple, right? So by using this inverting integrator and then making sure that it just subtracts, right? Because remember, we wanted this equals Vn times 1s minus this times 1s. And then, we got the low pass. All right. So but still, with this structure, just this one integrator, I can get a low pass, I can get a high pass, but I still can't get complex roots. All right. In order to have complex roots, you have to have at least a 2nd order circuit, right? Now that was a lot right there. Any questions before we move on?
Yes, I got a question.
Shoot.
Okay, it's about the spot where we connect essentially the second part of the circuit to essentially VR. Why exactly do we connect it there?
Can you shout out the color of the line near what you mean?
Oh, it's purple.
So around here?
Oh yeah, just slightly lower. Oh yeah, that one. The one that we use to create negative feedback.
Yeah.
Yeah, why don't we connect it to where VF is and right close to where VN is? RF and
Right here?
RF and RN. Yeah, why don't we connect it there?
As opposed to where else? That'll help me. That'll guide my answer.
essentially as opposed to anywhere, as opposed to essentially higher, like right above, like above our in.
Okay, so let's go back to, I'm gonna answer this one. Let's go back to nodal analysis, right? This is all the same thing. So I could connect it here, 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 anywhere in there is the same connection. Okay. Anywhere where I've just highlighted. Now, if I connect it here to ground, well, now I've just connected it to ground, right? And that's just the load. There's no negative feedback at that point. And of course, if I connect it on this side of the resistor, now the input is going the other way, and that's a mess. Did that answer your question?
I actually believe so. Yeah.
Okay. Now,
Another one.
like, yeah, no, just like, here's the thing. This is going to happen a lot, right? I'm going to have in, and then I'm going to have a lot of feedbacks, right here. And I tend to, this will be like A1, A3, A5. And what happens is when I draw it like this, you'll see I get less crossing of wires. Okay. All right. These are coming from elsewhere. That'll be to ground. All right. I just have a way of drawing it that over time just seems to make a cleaner schematic. Okay.
I have another one.
All right. So Juan, yes, this resistor does need to be greater than 2K because think about it. This op amp is now driving this circuit, and at high frequencies, this capacitor will appear like a short, but in a way that doesn't even matter because we're at a virtual ground here, and that 100K is its own load. And then coming around the other way, this is driving a capacitor, right? Which at high frequencies acts kind of like a short. And then I would use superposition and then short this end of the 100K. So I'd have like a 100K load this way, but then I'm also driving this 100K load, right? Which again, in superposition, these two would become in parallel and would be smaller, but still I'd have that 100K there. Okay. And there might have been another question that I didn't. I might have cut somebody off.
Oh yeah, it's me. Yeah, I was saying that if you go back to the second slide, if you change the position of 2, how are you gonna get the H?
This slide?
Yeah, if if you change the position of 2, put on the 1, how you gonna get H?
I mean, 1 was always here, 2 was always here.
Yeah, like one of the homework said that if you have Y is where 1 is, and X is V in, how you gonna get the function of the transfer?
I'm sorry, you're kind of breaking up a little bit.
So if you take Y, put where 1 is, and how you gonna find the Y of X? Yeah.
Even if I call that the output or
Yeah.
Y,
Yeah.
or I take this one.
Yeah, that one does not exist.
No, it exists. They exist at the same time. Let me put it to you this way. I mean, I derived it out, so you can see that. But if I take my oscilloscope and put one end here and the other end to ground, now I'm taking out the high pass. If I put my oscilloscope here, one lead here and the other end to ground, I'm getting a low pass. And if I have a 2-channel oscilloscope, I can look at them at the same time.
So in the reality, how this look like? Is just open or just there's a physical circuit like this?
In reality, a circuit like this.
Okay.
An op amp with an advanced summer and an inverting integrator. This is the real circuit of this system diagram. This is the real circuit of this system diagram, except it's really minus. And so we're actually adding it, but it turns out to be the same. Okay. Now, you'll see that to get it to be non-inverting, I actually have to add that. This will be minus low pass, and that'll just be high pass. Okay. Okay, I kind of got to move on. So today's lecture, where so these notes are this Google Doc, right? Although what I just went over was kind of a combination of a few lectures, all right? But now I need to talk a little bit about high pass, about RLC filters, okay? So for the series RLC, okay, we have R, L, and C, right? Now you can see that there's one mesh, right? But really, if I want the output here, I just use voltage division. And impedance. All right. Now, what I'm not showing is you really should have some kind of output buffer here to isolate whatever's going on over here so that it doesn't change your filter characteristics. So we have 1 over SC, R plus SL plus 1 over SC. Now we need to be in that polynomial format, right? So I know this is a second order circuit, so I'm gonna have to have something second order here, right? So I have no S, S to the first, 1 over S, which is definitely not helpful. So I'm gonna multiply through by S. And I'm gonna start to rearrange things. All right. Now, again, this is mathematically correct, but part of that polynomial format is that the highest order of S in the denominator has to be multiplied by 1. So it's multiplied by L. That's not going to work. So then I have to, I'll pull that out. Okay. And now I can choose R and L and C somewhat independently. I can get complex roots now because I have 2 different energy storage elements. Now, what did this look like on your Bodhi plot? Well, it's better to use this in a different form, to convert it into this form, which is unique to the second order thing, where omega naught squared equals 1 over LC, right? And 2 zeta omega naught equals R over L. And zeta, just to refresh your memory, is a damping factor, right? And you can see that if zeta is 1, I get S squared 2 times omega naught plus omega naught squared, which is basically 2 repeated real roots. If zeta is greater than 1, it's fairly easy to see I'm going to have 2 different real roots. But if zeta is less than 1, you can see that the roots, I mean the poles, excuse me, every time I just said root, I was saying meant the root of the denominator, otherwise the pole, okay? Sorry about that. So anyway, you're gonna get a complex number. But how do you control things? Well, this is your omega naught squared, and you have an equation, and then here is your other equation for R over L, but really you've got omega naught and zeta, 2 things, but you've got 3 unknowns. All right. So I'm going to walk you through an example. But just last time, right, we had an integration constant, which is 1 thing, but you need to know R and C, which is 2 things. And I told you to pick the capacitor and then calculate a reasonable resistor. Well, in this case, you're going to pick the inductor and then calculate a capacitor and then calculate the resistor and see if everything is reasonable from there. Excuse me. Let's say no. Just tell no. Okay. So, and the reason why we choose the L, then the C, and then the R is that there's a lot fewer choices for inductors than there are capacitors, and there's fewer choices of capacitors than resistors. All right. Now, I'm not gonna, these are all these are derived in my notes. Okay. But you can get the band pass, low pass, high pass, and notch. And what I'm going to do is just redraw this a little bit, or just redraw it. Okay. So no matter what, the denominator is always the same. But if I take my outputs from here to here, or from here to here, or from here to here, right, it will affect the circuit. Well, what if this is my output, right? Well, it's the voltage division again. So it's really ZL plus ZC, because it's in series, right? I could just turn that into an equivalent circuit, right? And then I have ZL plus ZC plus ZR. All right. I have SL plus 1 over SC. Okay, so I can't really have this here. I mean, I could have the 1 over C, but I can't have the 1 over S. All right. So I am just going to multiply everything by S over S. And so I get S squared L plus 1 over C, S squared L plus SR plus 1 over C. And in this case, right, I got to take out the L, right? And I take out the L from here. All right. And what that becomes is this. But notice, these two things are added. So this series circuit, right, is actually giving me the parallel architecture of a notch filter, because S squared by itself would be the high pass. Omega naught squared by itself would be the low pass. The denominator is the same, and we're just adding them. All right. But, and then just a word to the wise is, once you design the low pass, you have C, L, and R values. Well, if you want the high pass, take the output over the L. If you want the band pass, take the output across the R. But these values don't change because the denominators aren't changing, right? And if you want the notch, well, just take it here, which of course it could be this or so if I take the output from here or here, right? It doesn't matter what order, okay? So you have a link to this note, and I'm just going to walk you through it. All right. So there's a Python program, right? That is the cutoff frequency is 50 kilohertz, order set to 2, and then it gives you these constants. Okay, and you'll learn this in lab too. All right. So then it's a matter of, well, those are the constants. This is the transfer. Oh, A1 equals R divided by L. A2 equals 1 divided by LC. All right, so choose the inductor, calculate R and C. And yeah, you want to keep the impedance, right? Which if I put a ohm meter, an impedance meter from here to here, no matter what the frequency, right, I want to be greater than 2 kilo ohms. But these impedances are opposite, right? One's positive, one's negative, and frequency for which these cancel out. So the only way to guarantee a minimum impedance is to set R1 to it. All right. So now, yeah, I derive all that. that's an aside where I just derive all that. And it just turns out, yeah, you gotta keep it R is R. So now I'm going to show you the first attempt where I'm going for 50 kilohertz and I want 10 microhenries. I just choose it. All right. I calculate the capacitance, 1.1 microfarad. That sounds reasonable. I can buy that. R, 4 ohms. Oh man, that's too small. Right. Now I could keep guessing, or I could say, well, our minimum is 2 kilo ohms. A1 is that. So L should be 4.4 millihenries, but I don't necessarily have that, right? Remember, there's not many choices. But then now I know that if I use 5.6 millihenries, which you can buy from Anchor Electronics, right? Then I calculate C, 1.8 nanofarads. That value does exist. Then I calculate R, and it's, 2.5 kilo ohms, right? And here are some charts for inductor values you can use, right? So here's an RLC circuit. Those are my R, that's my L, that's my C. Way I simulated it is frequency low, frequency high, so that it always comes right in the center. Now, I just want to take a moment and talk about omega naught. Now, this is a low pass filter. It's second order. You can see that because the phase goes from 0 to 180, right? And you know that the phase will be minus 90, right? And that's used to be where you pick things off. But omega naught is not necessarily the break point. Okay. Now, in this case, it is, because it's a second order filter and it's a Butterworth filter. And it's designed to be like that. But if I had I could have the same omega naught, but have 2 different break frequencies, actually, right? Because I have 2 real poles, or I can have very complex poles where this kind of resonates and calms down. All right. So you can't just say omega naught is the break frequency. All right. Although for Butterworth, it is. All right. Just don't. It can bite you once in a while. All right. But the point of the Butterworth is that this dip here is always 3 dB and this is always flat. And it can be 8th order. The higher order it is, this just gets sharper. So there's the simulation of that. All right. So with that, you should be able to do any RLC problem. Okay. With those examples. And by the way, I have to redo that homework with just different values. All right. Now, we talked about simple high and low pass filters, putting things in series, right? Which pretty straightforward. We've talked a little bit about feedback, right? But now we're going to put all of them together into this technique for which you can generate any transfer function, right? With just a summer and a bunch of integrators. Now in the book, they talk about something called DF1, which isn't really used in op-amp circuits. He mentions it because it can be used for certain reasons in digital filters, like your 112, all right? But the important thing here is here's a summer, right? That's the advanced summer, just like we've seen before, right? And yeah, we have a summer over here, just in case. And then look, we have 1 over S's, okay? So that's an inverting integrator, inverting integrator, inverting integrator, inverting integrator. This is the denominator terms. And this will be the numerator terms, all right? Now, it's actually pretty straightforward if you just kind of follow the process. It's very algorithmic, all right? You basically, here's a generic transfer function. Here it's, higher order, right? And yeah, mathematically, you turn it into something with integrators. All right, that's S to the 4th. So then I multiply by 1 over S to the 4th by everything. And so then I get B naught, this over S, left over squared, this over S cubed, this over S to the 4th. Same thing here, right? So by multiplying by 1, I convert this into something that now I can use this picture. But the way I don't really bother with that anymore. I just happen to know that this will be 1, and it'll just come out from here. And then that the second integrator, that'll come out of the second integrator, right? And this will come out of the 3rd, this will come out of the 4th, and that'll come out of all of them. So it's just kind of reverse, all right? But that's how you convert it into integrating format. It's got a procedure. It's almost like, you could put this into Python, right? And it would draw the circuit schematic automatically for you because it's so algorithmic, all right? It doesn't use any inductors. And so it's the same thing. You kind of choose a C value that you think will work, and then you start calculating the resistance values of the integrators, and then you tend to keep everything the same for the advanced adders. So before, right, we had an input and we had one feedback node, right? But now we have an integrator that's positive. And this integrator is inverting. We bring it in on the positive side to keep it subtracting. But now I have an integrator, inverting integrator times inverting. Well, now it's positive. Well, I got to subtract it. Well, now I bring it in on the inverting side of the sum. Well, now I have 3. I have minus something divided by S cubed. Well, I want to keep it minus, so I bring it in on the positive side. I have a positive number divided by S to the 4th. I need to subtract it, so I bring it on the inverting side. And then here's the final summer where we're adding the B's, right? Well, the B's, these integrators generate the A's and the B's, but these are being fed back negatively. These are just being, they call it feed forward, or it's just, you're just adding it. So they have to all be positive. So this one's negative. Oh, I flipped it. So just so you know that that's negative here. That's a negative sign. Probably shouldn't do that because it'll confuse. So this one's negative, so I have to invert it to make it positive. Other odd one is negative, I have to make it positive. And then the positive ones, I just keep on the positive side. And that these resistances here, what I use to set the scale, the integration constants, and then here, everything is usually like the same value. And 1, 2, 3, 1, 2, I need a dummy. I add the dummy. All right. But that's, let me just walk you through an example. All right. Again, cutoff frequency of 10 kilohertz. I set the order to 4. So this is my highest B constant. And then here are my A constants that you can make out here. So that's really omega naught to the 4th. And this would be omega naught to the 4th. But those damping coefficients like zeta are only defined for second order systems. For higher order systems like this, you would just say, do you have complex poles or not? Right? Anyway, so I'm going to need, it's 4th order, I'm going to need 4 inverting integrators, right? And I have to subtract every term in the denominator, right? 1, 2, 3, 4. 1, 2, 3, 4. They get subtracted. And then the output is connected by something that here. So basically, the way to remember it, if I divide this by s to the cubed, this is divided by, s to the 4th. This is divided by s to the 4th. So I have something over s to the 4th, something. This is s over something over s to the 4th. I'm going to take my output there, right? Now, then what I do is rather than have everything 1, and then in the advanced summer scale everything with gains, I make everything -1, and I just say, oh, that's A1 divided by S. But now this is A1, it's not 1, it's A1 divided by it. So now this is A2, but if I take my scale factor A2 divided by A1, it'll come out, it'll give me A2 here. Then if I keep this going, right, this ultimately is A3 divided by S cubed. This is A2 divided by S squared. This is A2 divided by S. And this would be A to the 4th, A4th divided by S to the 4th. I manipulate this out so that here, okay, I have a 4th order circuit. I have 4 inverting integrators, right? I chose a common capacitor, 1 nanofarad, right? And then R1 divided by C1 is actually my A1. It comes out here. So it's already scaled by A1. So I just have 100, 100K. The gain is 1 here. Now then I have 12. The gain here is 1 divided by these 2 divided by these 2, which ultimately is A2, right? Which then it's positive. I need to make sure it's negative feedback. I bring it here. Well, now all of these multiply through to give me A3, but it's negative, so I want to keep it that way. All of these are time constants multiplied through give me A4. That's positive. I bring it this way, and that's the out. Now on the exam, right, you've got to draw, if it's a 4th order circuit, you got to draw 4 inverting integrators, and you have to make sure that you got your minus and your plus, the capacitor here, the resistor here. right? The negative ones have to go in on the positive side. The positive ones have to go in on the negative side. And you've got to label V out. Because if I say low pass filter and you pull it here, well, in fact, that's the high pass node, right? There's, low pass nodes. So if you don't label V out, the problem's like wrong. It's like 100% wrong, okay? Because open book, open note, right? You've got this picture. That's a generic picture, right? You've got to know where to take it out, all right? Anyway, I have a file. I calculate everything in Excel, right? And so I can do it that way, right? Now, yeah, here's the same kind of thing, 10 kilohertz, but I set the order to 6. All right. I calculate everything through. All the capacitors are bigger than 2K. 1, 2, 3, 4, 5, 6, right? Negative, negative, negative. So it stays positive. So bringing it on the positive. Positive, 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 bringing it on the negative. I have 1, 2, 3, 4 inputs here. 1, 2, 3 inputs here. I got to add a dummy. And that LP here means I'm taking it off of the low pass. But you actually get the high pass for free, if you will. Okay. I have notes where I just do study, thing after thing after thing. What if there's an odd number of stages? All right. What this doesn't show is what if I want to add something? Okay. Now, I will probably do another case study, okay, on Wednesday, but we're going to start talking about the gain bandwidth. And the thing I think to remember is, like, learning where the Bode plot comes from can be very difficult. But actually, doing the Bode plot, the asymptotic Bode plot, if let's just say you were following instructions and you didn't really care about imaginary numbers or anything, right? It's actually kind of easy to draw if you're not encumbered with trying to think about it, right? This, right, it's a, Bode plot, but the rules are really simple, right? Every time you go past a break frequency that's a pole, subtract 20 dB per decade slope. Every time you go past a break frequency that's a 0, add 20 dB per decade, right? And then there's a few rules. If you start off with a 0 at 0, that's a special case, all right? But really, the code right here is just, where's the phase going to be? And actually the phase is a little trickier, right? But really, where's the pole? If it's a pole, add 20, subtract 20 dB, 0, add. The rest of it is kind of like, well, make sure there's no repeated information so the plot doesn't look funny, and make sure the plot extends beyond the poles and roots of interest, and then, make it pretty. This is really just an algorithm, all right? Yeah, but that's pretty much it for today. I know that's a lot, but in order to do it, you're probably just going to have to do a few repeat the work of the case studies, right? And then go do the problem on your own. Okay? Any questions? All right, guys. Take care.
Have a good day. Have a good day, Professor David.
Thank you, Professor. Have a good day.
You too. You too.
Yeah, Professor, I